Let's answer part A. So here we determine the mass of anteater tronium after 150 years. So here we can determine this by two methods. I'm going to explain both methods. Let's see, this is method one. We can see this is a conceptual method. In this method, we consider this initial amount is 1024 milligrams, and we are given that the half-life of an plutonium is 50 years. And this means every 50 years the amount will get reduced by half. So when we have 1024 milligrams at the beginning, that is after 50 years, this will get reduced to half of 1024. You can divide this by 2, and this gives 512. Now let's calculate for another 50 years. So this is 50 years. That is for another half life. This amount will get reduced by half. So we have to divide 512 by 2, and this gives 256 milligrams. So far, we have calculated for 50 plus 50, and this equals 100 years. That is, after 100 years, the amount of anti-plutonium present will be 256 gram. And since we want to find the amount after 150 years, we calculate for one more half year. That is a half period. So we find for another half life, 50 years, this amount will get reduced by half. So it is 256 divided by 2, and this equals 128 milligrams. So this is the amount present after three half-life periods. That is, this is first, and this is second, and this is third. And if you add all the three half-lives, each half-life constituting 50 years, we get 50 plus 50 plus 50 equals 150 years. So this is the amount of the anteater tonium. That is, this is the amount present after 100. I'm sorry, this is 150 years. It's not milligram. It is 150 years. The amount present is 128 milligrams. Now let's see method 2. And this is a formula method. This is a more general way of determining the amount of substance after t years. So I write down this formula, that is AF equals A naught e raised to the power of negative kT. Here AF represents the final amount of the substance. You say this is a final amount, and A naught represents the initial amount. This is initial amount, and K is the constant to be found, and T represents the time in corresponding time units. It could be years, minutes, or seconds. Here it is in years, so this is time in years. So let's use this formula method. We are told that the initial amount is AF. So I'm sorry, the initial amount is 1024 grams. So we know that it represents A0. A0 equals 1024 milligrams. And we have to determine the mass after 150 years. So we know that T equals 150 years. And we have to determine EF, that is the amount present after 150 years. But before that, we have to determine the constant K. I'm going to write another formula for the constant K. This is natural logarithm 2 divided by T half. This T half is the half-life period of the substance. For any half-life period, we can utilize this formula. In fact, this is proved for any half-life period. the value of constant k is found to be natural logarithm of 2 divided by T of. T of is the half-life of the substance. So here we are given that the half-life of antideutonium is 50 years. So we know that T half equals 50. So our first task is to determine the value of this constant k. So let's find the constant k. This is k equal natural logarithm of 2 divided by T half is 50. So we got the expression for k, which equals a natural logarithm of 2 over 50. Now I'm going to utilize this formula and substitute all the values including the k. So let's write this equation. This is final amount equals initial amount times e raised to the power of negative kt. We know that initial amount is 1,024 milligrams. So I substitute 1024 for a naught, and e raised to the power of negative of k is natural logarithm of 2 over 50. So I put natural logarithm of 2 over 50 and multiplied by t is we have to find the mass after 150 years. So t equals 150. We plug in 150 here. You see that we can do some cancellation here. Since these two are a product, we can cancel this 150 with the 50, and this goes three times. So it's basically, we can simplify this. So we get this is the final amount or the amount after 150 years, and this equals 1024 e raised to the power of negative of natural logarithm of 2 times 3. So this is what we have. Let me show you how to simplify this. So we have natural logarithm of, that is negative natural logarithm of 2 times 3. This we can, this is nothing but a product. So 3 times of negative 1 is negative 3 natural logarithm of 2. And now using the power rule of natural logarithm, we can take this negative power, or if we, even if it is a positive power, we can take it inside the natural logarithm and raise it to the power of the number represented in natural logarithm. So this is basically equal to natural logarithm of 2 raised to the power of negative 3. We know that 2 power negative 3 can be written as 1 over 2 power positive 3, and this in fact equals 1 by 8, because 2 power 3 equals 8. So I'm going to plug in here. So therefore this becomes a natural logarithm of 1 over 8. So we simplified this expression. Let me substitute here. So this becomes 1024 e raised to the power of natural logarithm of 1 over 8. Now we see that this exponential as well as this natural logarithm, they both are inverse to each other. So they cancel out, and which gives 1024 multiplied with 1 over 8. And this equals 1024 divided by 8. This equals 128. So we found that the amount of substance present after 150 years equals 128 milligram. So we can now clearly see that in both methods we got the same answer, that is the final amount is 128 milligram in first method, that is this method, as well as in method 2 also we have obtained the same final value, which is 128 milligrams. Let's answer part B. So we now find the time it takes for the substance to decay to 30 milligrams. So here I'm going to use this method too, that is the formula method. So first let me rewrite this equation by plugging in the value of k equals natural logarithm of 2 over 50. So therefore we write this equation AF, and this equals A0. We can plug in for A0. We know that it is 1024 milligrams. So it is 1024 e raised to the power of negative k, that is negative of natural logarithm of 2 over 50 times t. So we put this t. So this is the equation that we have to utilize. And since we wanted to determine uh, the time, so basically we have to determine time when the final amount is 30 milligrams. So we say that we have to find the t when AF equals 30. So let's plug in AF equal to 30 here, and this becomes 1024 e raised to the power of negative natural logarithm of 2 over 50 times t. Let's simplify this expression. That is, we are going to simplify this complete expression. So let's do it here. We have natural logarithm of 2 over 50 times t. So this can be written as natural logarithm of negative natural logarithm of 2 times t over 50. And in fact, I can put this in front. Since it is a product, I can rewrite this as negative of t over 50 times natural logarithm of 2. Now, when we use the power property of natural logarithm, we take this number in front of the logarithm to the power of 2. So therefore, this becomes a natural logarithm of 2 raised to the power of negative t over 50. So this is the simplified form which we are going to replace. So I'm going to substitute it over here. So this becomes 30. In fact, I can now divide by 1024 on both sides. So this will become 30 divided by 1024. And this equals, we will have e raised to the power of this simplified expression, which is a natural logarithm of 2. I put natural logarithm of 2 raised to the power of negative t over 50. I have to write this specifically in this form so that I end up in a situation where I can cancel this e with this natural logarithm. So the because they both are inverse to each other. So this means we get left side we will have this number, that is 30 divided by 1024, and this side equals, since these two gets cancelled, we will have only the remaining part, that is 2 raised to the power of negative t over 50. Now we have to solve for t from this equation. Once again, we can apply natural logarithm to both sides. So apply natural logarithm. I'll just clear this up before we proceed. Okay, so let's apply natural logarithm to both sides here. We have a natural logarithm of 30 over 1024, and this equals natural logarithm of 2 raised to the power of negative t over 50. Now again we use the power rule of natural logarithm, so this power will come in front, so which gives, we now have this equation, natural logarithm of 30 over 1024. This equals, I put this negative t over 50 in front, multiplied with the natural logarithm of 2. Now to solve for t, we first divide both sides by natural logarithm of 2. So I'm just going to take this here and get it divided over here. So it becomes like this. I just divided this. We then have this expression, and on the right side we have this expression negative t over 50. Now to solve for t, we have to multiply both sides by negative 50. So when I do that, I can see that I can put this negative 50 here times natural logarithm of this expression. So we will have only t over here. Since we multiplied by, sorry about it, since we multiplied by negative 50, we'll have only t here. So we got the expression for the time. Uh, Let me rewrite this in a simplified form. So this equals, can write down this t as negative 50 times of natural logarithm of 30 over 1024, divided by natural logarithm of 2. So this expressions gives us the time to evaluate given the final amount is 30 milligram. That is when the substance decays to 30 milligrams. So we can consider this as the expression to determine the time. And in fact, when we plug all those values on the right side into the calculator, we get the time it takes is about 254.655470 is just a recurring number. So this is approximately 254.655470 years. And if you need the exact expression, we can consider this as expression. And in terms of values, we can consider this time as 254.655470 years. Let's answer question 7. So here we are given the cost in terms of dollars. That is, a unit of cost is dollars, and the S represents the square feet. The unit of S is square feet, and we have to determine the unit of C prime of S. So this is basically the derivative of the cost function, that is d of C of S with respect to the S. So it's basically the unit of the numerator, that is the unit of cost function is dollars, and the unit of the denominator, which is the S, and this is in square feet. So I can put this as feet square. So therefore we say that the unit of C prime of S, and this is dollars per feet square, or we can write down this as dollars per square feet.